Welcome to a lesson with Dr. Powell. Let's take a look at how these little differential symbols, dy and dx, can be useful sometimes in measurement for measurement purposes. For instance, suppose that you're trying with some instruments, you're trying to measure the height of a building, and you know your distance away from the building is 50 feet. And suppose that your angle right here, suppose it's 20 degrees, and you want to be able to and you know that your instrumentation could be off just slightly. Maybe you have a 1% accuracy, so your error could be off by 1% of what you've actually calculated. So then the question is, how much off could you be here in your actual measurement? This is where derivatives come in, because there's some variability. We're going to use we're going to make a couple things variable. We're going to fix 50 as constant, but what's varying in the situation is this angle theta, and this height, call it h. Okay. All right. So first of all, really what we're trying to do is we're trying to investigate some relationship between d theta and dh in the relationship between h and theta. So if theta changes a little bit, how much does h change? So kind of thinking about that will enable us to really get at this, get this well. You see this 1% error. So we have 20 degrees, right? And so 1% error means that your angle could be off by 1% of what you measured. So 1% of what you measured, just take a fraction or multiply by 0.01 of that. So you end up getting 0.2. So that means your d theta in degrees will be about 0.2. However, when we take derivatives, our derivative formulas have actually come from the idea that we were measuring in radians, that nice inequality that we had for sine that determined the limit of sine over sine of h over h even. That all had to do with radians. So we really have to be careful here and change everything into radians if we're working with derivatives, because that's where our derivative rules come from. So we change, so we can change, so this is 0.2 degrees, but now we need to change the 0.2 degrees to radians. Okay, so what we do is we think, okay, so 0.2 is that fraction of 180, and so that's the fraction of pi that we need. So we have, so d theta will be equal to 0.2 pi over 180. I'm just going to leave it like that. I won't round or approximate or anything. I'm just going to leave it like this for now. That's what d theta is, and it's in radians. All right. Now we got to find the relationship between d theta and dh. Well, first, let's come up with an equation that relates them. We know that the tangent of theta is equal to h over 50. This is really nice. Okay, so let's just take, okay, so this is really nice. We can work with this. In particular, we could take the derivative of both sides with respect to theta. That would be fine. There's more than one way to do this. We could even just have an external variable parameter if we wanted to, and take a derivative of both sides with respect to it. And that would be fine too. We're going to get the same relationships whatever we do here in this case. But here, let's just take the derivative of both sides with respect to theta. Over here, we're going to end up getting secant squared theta as a derivative with respect to theta. And on this side over here, we're going to end up getting 1 over 50 but then times, okay, h is just variable, so you just get 1, but then you have to multiply by the derivative of h because h is like a chunk. It's something, it's a function of theta. So we just simply get the derivative of h with respect to theta, which I will write like this, dh over d theta. So quite literally, we're taking a ratio, dh over d theta is a ratio of rise on the tangent line to run on the tangent line. So to compute the relationship, an equation that relates dh and d theta, take this as a ratio and assume that we're dealing with a positive run for theta, and we can multiply both sides by d theta. So we end up getting secant squared theta is equal to 1 over 50, and see, but we multiply by d theta over here, okay, dh. So we have a nice relationship between dh and d theta. In fact, we can multiply both sides by 50. And we get 50 times that is equal to h. Okay, or dh, that is. Okay, so then with d theta being this, we can compute what dh is very nicely in this particular case. Yeah, okay, so let's go to that point. And theta, what do we use for theta? We use just the same, we use for theta the exact same value that we have here, the 20 degrees, but converted to radians. Or we could do degrees as long as we're in radian mode. Degree mode, that is, and that's just fine. So we get that dh, so how much off can we be? So dh, we get that would be equal to, so plugging in what d theta is, so 50, right there in radians here, so 0.2 pi 1 over 80. So this needs to be in radians because we're taking derivative with respect to radians here, so we had to make that conversion to get what d theta was here. Now over here though, yeah, we can plug in whatever we want, as long as the calculator converts it in the right way. But essentially, if we're in radian mode here, when we plug in the calculator, I'll just kind of pretend what we are. So that means we have 20 pi over 180 to do the conversion. But really, it doesn't matter. You could just stick, if you're in radian mode, you could do that. If you're in degree mode, just do 20. It'll give you the same result. And that's equal to, that's dh. Okay, so that's perfect. So if we compute this, we'll know exactly how far we are off. How many, this is a measurement of how many feet we're off. Okay, in that calculation. So if you work that out, you should be able to see what that is. Thanks for watching.